Today in Lab 2, I will be discussing the motion of a falling object. The objectives of this lab is to record a falling object in motion using Tracker, model the object in motion with drag force and without drag force in VIDLE, compare the position versus time of the experimental and prediction models. From the previous lab, we discussed Newton's second law, which stated that velocity final equals velocity initial plus net force over mass of the object times the change in time. And when an object is in constant motion, the final velocity and the initial velocity equals 0. In today's lab, there are other forces acting on the object, so that net force equals the weight force plus the drag force. The object's weight force is the mass of the object times the acceleration of gravity of 9.8 meters per second squared times the unit vector that shows the direction of that the object is falling. The object is falling towards the ground, so there is a negative sign. The turbulent drag force is a force that the direction is always opposite to the direction of the object's motion, and whose magnitude is proportional to the square of the object's speed. The B is the drag coefficient and is proportionally constant to the magnitude of drag force. The system being used today in Tracker is a square tissue box, while the surroundings is the air and the environment around the box. This is what the object looked like when it was in motion. Tracker also created a graph, and this graph compares the y to the time. And we chose y because it's falling in the y direction. Only slides 17 to 27 were manipulated to not add any extra force from the drop, as well as the axis was tilted to create better data. In VIDLE, the given code was manipulated. So the mass of the object was changed to 0.199 kilograms. The position was changed to the initial position found in Tracker. The time step was set to 0.001, so this calculated the small change in time. And the J hat was changed to 010 because it was a drop in the y direction. The B was manipulated by viewing how close the y position of the model was close to the final y position in the experiment when the code was run. The code was manipulated that the final time was added along with the weight force, the drag force, the net force, Newton's second law, the updated time, the position, and the updated time, as well as arrows to show the drag force. The arrow scale was found by doing 2 divided by the mass times the gravitational constant. When run, the prediction model with drag force should look similar to this. This shows that the drag force is in the blue while the weight force is in the yellow. And this shows the position and time. This shows how similar it is to the final y position and how we got the b position. Then the prediction model was found by editing out all the drag forces, and the model should look somewhat like this. The computational model shows that there is no drag force on this object, while there still is the weight force. This is what the time versus position would look like on this graph. Google Spreadsheet was used to make a graph of the data. The blue dotted lines are the experimental model, the yellow is the predicted model without drag force, while the red is with drag force, the prediction model. The graph shows that the experimental and prediction model with drag force are quite similar with a little variation in the velocity. This is due to possible errors such as the axis on the tracker not being as tilted as necessary, as well as the program not detecting the center of mass correctly. Human error includes not dropping the tissue box straight with no extra force from my hand. The graph for the prediction model with no drag force shows a higher velocity since the slope of the line is steeper than the prediction model with drag force. question might be, what is the terminal velocity and which models have it? Well, as an object falls, it picks up speed, and an increase in speed leads to an increase in the amount of air resistance. Eventually, the force of air resistance becomes large enough to balance the force of gravity. At this instant in time, the net force is 0 newtons, and the object will stop increasing. So all these graphs show that there was a constant line, so F net equals 0. Another question is, what if it was initially thrown downward instead of from rest, and what would the terminal velocity be? When the velocity is manipulated by being changed from 0, the graph that is being made is quite constant with little changes. The terminal velocity would be greater since there is a steeper slope. The conclusion is that this lab effectively showed the different things that we were trying to see in this lab.